Okay. So we just talked about something called the effective nuclear charge. And effective nuclear charge, we just found how to calculate it using this latest rule. Now, when we talk about this effective nuclear charge, what it tells us is that how much attractive force would the nucleus exert on an electron. It tells us how strongly an electron is held by the nucleus. We took certain examples yesterday, and the examples were sodium, potassium, magnesium, calcium, aluminium, and gallium, and let's say India. So these were the examples that we took yesterday. And in these examples, we found that sodium had a screening or shielding constant of कितना था इसका? 8.8. Sodium had a screening or a shielding constant of 8.8. So its effective nuclear charge would turn out to be the atomic number, that's 11, minus 8.8, that will turn out to be 2.2. So sodium has an effective nuclear charge of 2.2. Potassium, the atomic number is 19, the screening constant turned out to be 16.8, and you find again it turns out to be 2.2. Okay. In magnesium, it will be 12 minus 9.15, that will come out to be 2.85. And in calcium, it's going to be 20 minus 17.15. Again, it comes out to be 2.85. In case of aluminium, here it turns out to be 13 minus 9.5. It comes out to be, in gallium, it is 31 minus 26. Here it comes out to be 49 minus 44. So these are the values of effective nuclear charge. Okay. Now, one thing you can very clearly see from here, that as we move across the period, the effective nuclear charge increases. As we move across the period, the effective nuclear charge increases. Is that clear? Yeah. Effective nuclear charge is a comparative term. That is, this has a higher effective nuclear charge, this has a lower effective nuclear charge. In fact, when we talk about something called atomic number, this also is the dimensionless quantity. It is just the number of protons. So it does not have any dimensions with it. So effective nuclear charge cannot be used to find the attractive force exactly. It can only be used to compare the forces in the various elements. Is that okay? It is for comparison, not for the exact value. So, these are the effective nuclear charge, and when we move across the period, the effective nuclear charge is increasing. और एक और important बात देखना, that the effective nuclear charge is increasing by a definite value. From here to here, the effective nuclear charge has increased by 0.65. 0.65. 0.65. Now, if you need to know why it increases as you move across the period, then you can very easily understand that what we have done is, when we are moving across the period, we move one step, we add a proton in the nucleus, and we are adding an electron in the same shell as the outermost electron. Increasing a proton in the nucleus increases the atomic number. Well, effective nuclear charge is Z effective. In some books it is written as Z star. that is equal to Z, that is the atomic number, minus the sigma or the screening constant. This is atomic number. Now as we are moving across the period, the atomic number increases by 1 unit at each base, whereas the sigma is increasing by 0.35. We are adding the electron in the same shell, and in the same shell the electron has a screening constant of 0.35. Is it okay? It gives a nullifying effect to the nuclear charge by 0.35. So sigma increases by 0.35 at each step across the period, whereas Z increases with 1 unit at each step across the period. बताऊंगा वो एक step नहीं है बेटा. That's not one step. Now here the Z effective increases by 0.65 at each step in S and P block. S or P block में if we move, it is going to increase at each step by 0.65. Is that clear? Any doubts? S block और P block में हमारे पास S block, P block, D block, F block है ना, तो S block और P block के अंदर when we move across the period, it is going to increase at each step by 0.65. ठीक है? ये S block था. ठीक है. अब एल्यूमिनियम के आगे अगर मैं सिलिकॉन लिख देता हूँ, सिलिकॉन और एल्यूमिनियम के बीच में भी 0.65 का आएगा. ठीक है. Now we have to understand that when effective nuclear charge increases, what is going to happen? One thing is absolutely clear. Effective nuclear charge is how strongly the nucleus attracts the electron. Okay? It is how strongly the nucleus attracts the electron. That is what we call as the effective nuclear charge. If the nucleus is going to attract the electron towards it, the electron will move nearer to the nucleus. अभी तो कोई कहने वाली बात थोड़ी ना है कि अगर तुम किसी बोतल के ढक्कन को खोलने की कोशिश करोगे तो क्या होगा? ढक्कन खुल जाएगा. In the same manner, if the nucleus is going to attract the electron towards it, the electron will move nearer to the nucleus. And if the electron moves nearer to the nucleus, the atom is going to shrink. Is it okay? So as we move across the period, the atom shrinks, that is, the atom becomes smaller in size. Is it okay? Ashwini, is that okay? So as we move across the period, the size of the atom decreases. Clear? Any problem in it? Fine? Is it okay? So as we move across the period, the atom size decreases. Clear? Okay. So this is the effect of effective atomic number. Second, let us say we want to remove the electron from the atom. To remove the electron from the atom, an energy needs to be provided. This energy is called ionization energy. The energy required to remove the most loosely bound electron from the outermost shell of a neutral gaseous isolated atom is called ionization energy. Now, isn't it very obvious that as the hold of the nucleus towards the electron increases, this energy which is required to remove the electron from the outermost shell also is going to increase? And so, ionization energy also increases across the period. Is that clear? Any problems? Then, the third thing happens to be electron affinity. Now what's electron affinity? When we add the electron into the nucleus, it is something like we are adding a negative and a positive. So when negative moves towards the positive is the effective nuclear charge. So when the negative moves towards the positive, it is going to release energy. And we have talked about that in the formula. Is it okay? Ranjul? So as the electron moves towards the nucleus, it is going to release the energy. Obviously, more is the positive charge, more would be the energy released. Because the energy released is nothing but K Q1 Q2 upon R. That is the energy. Yeah. So if the Q1, that is the nuclear charge, or rather I should say not nuclear charge, but the effective nuclear charge, as this Q1 is going to increase, the overall energy released is going to increase. So as the effective nuclear charge increases, the energy released on adding the electron increases, and this energy which is released is called electron affinity. So as we move, affinity, electron affinity. Is that okay? Clear? So as you move across the period, the electron affinity also generally increases. Redux? Any confusions here? Is that clear? Then we have fourth thing, very important, which is called electronegativity. Electronegativity. Electronegativity is how strongly a nucleus can attract the shared pair of electron present between the two nucleus. Let us say we have a covalent bond. We have a bond between the two atoms. Now, whenever we have the bond between the two atoms, let's say A and B, their electron pair is supposed to be present in between A and B. There is a kind of a war between A and B to attract the electron towards themselves. A also is attracting towards itself, B is also attracting towards itself. Where this electron ultimately rests depends on the effective nuclear charge of the two. The atom which has a higher value of effective nuclear charge will be able to pull the electrons more strongly. Is it okay? Now this capacity of an atom to pull this shared pair of electron towards itself is called electronegativity. Is that clear? This is what we understand by electronegativity. If B is more electronegative than A, then this electron will be shifted more towards B than A. Is that okay? इससे बेटा लाइफ और डेथ का फर्क पड़ेगा और कुछ नहीं. Because now this A will be having a slight positive charge and this B will have a slight negative charge. There will be a charge separation and the entire property of the substance is going to change. ठीक है? अब अभी अभी तो बताया effective nuclear charge is the capacity with which the atom, the nucleus pulls the electron towards itself. क्या? और effective nuclear charge का एक example भी दिया था ना. The effective salary of your father for you, plus effective income of your father for you, how much you get. Right? मैं जैसे effective nuclear charge का बोल रहा हूँ, नाम भी मैंने change नहीं किया. As the effective nuclear charge increases, it is going to decrease the size, increase the ionization energy, increase the electron affinity, and increase the electronegativity. Are we clear with that? Ajay? There there might be a question that you want to ask. I don't know whether you want to ask or not, but still I'll answer that. When we are moving across the period, we find that the effective nuclear charge is increasing, and the reason is absolutely clear to us. That the nuclear charge is increasing by 1 unit while the screening or the shielding constant is increasing by 0.35. So there is a net increase of 0.65 in the effective nuclear charge. That's very much clear to us. But we need to find out that what happens when we move down the road. Here, the screening constant is 8.8, here it is 16.8, here the atomic number is 11, here is 19, but what we find is effective nuclear charge turns out to be the same. Does it mean that sodium and potassium have the same ionization energy, same electronegativity, same electron affinity, same size? Does it mean that?
Yeah.
No. It does not mean that, because while talking about the effective nuclear charge, we have not considered one very important factor. The Slater's rule have a flaw, and that flaw is they do not take into account the distance of the electron from the nucleus. Sodium, the configuration is 1s2, 2s2, 2p6, 3s1. Potassium, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. This is fourth shell and this is third shell. So when we move from sodium to potassium, an extra shell has been added. An addition of the extra shell would mean the distance from the nucleus increases. Okay? And obviously, the actual effective nuclear charge depends on the distance from the nucleus. So even if, according to the Slater's rule, sodium and potassium both are getting the same effective nuclear charge, in actual understanding, potassium has a lower effective nuclear charge than sodium. Is that okay? As we move down the group, the number of shells increase, which increases the distance of the electron from the nucleus, and therefore the effective nuclear charge decreases, although the Slater's rule predict that they are going to remain the same. Is that clear? As we move down the group, there is an increase in the number of shells, which increases the distance of the electron from the nucleus, which leads to a decrease in effective nuclear charge. Full stop. Hence, if two atoms have the same effective nuclear charge by the Slater's rules, then the atom which has more number of shells has a lower effective nuclear